Hello everybody, and welcome to our video on representing functions as power series. Now this is going to be sort of the culmination of everything we've been doing regarding series up to this point. So we talked about power series before, but now we get to see the power of being able to model the behavior of elementary functions through the use of power series. So what do I mean by that? Well, we saw earlier, and we just kind of touched on it and didn't talk too much about it, that 1 over 1 minus x could be written as a geometric series, x to the n minus 1 when n goes to 1, from 1 to infinity. And of course we know we can shift this index here, change this to starting at n equals 1, and then we just adjust our formula to be 1 larger with our n here, so x to the n. Now, this is sort of the standard way we write power series, starting with n equals 0, and that's because we think of power series as having this 0th term at the beginning, the 0 power term. So you should get used to now, when we're dealing with these power series forms, we'll use n equals 0 to infinity for x to the n a lot of the time, most of the time. Okay, that being said, I want to take a look at a little graphing tool here to show you the power of what this does for us in terms of modeling the behavior of functions. So let's pull this up, zoom out a little bit. So the graph here is the graph for 1 over 1 minus x. And what I've done here is graphed the partial sums for the series. So that series is 1 plus x squared plus x cubed plus x to the fourth, so forth and so on. But we're going to look at the partial sums one at a time. So this is that first term, just y equals 1. It's not a very good approximation for the function in red we see, but it does take the exact value at 0 here that this function does. All right, now we use the first two terms, y plus x, and notice this is actually the tangent line at this point at 0. So this gives us a tangent line approximation for the function. Now we look at 1 plus x squared. So now we've got a parabola, and we see this is becoming a better approximation for the function, at least near 0. And we add another term, x cubed, and again, that's better. So now I've got a little tool that's just going to go through adding more and more terms to this graph. And we're just going to look at what happens as I go from 0 to 20 terms here. So, hold on, I clicked the wrong button. There it is. Okay, so there's our 0th term. First, second, third, fourth, so forth and so on. And notice if we zoom in a little bit here, it's kind of hard to tell zoomed out. But every term we add, the approximation gets better further away from 0. So this is the big idea. We can take these functions and we can actually approximate their behavior with polynomials by using these power series representations for them. Now, if we take a look at the function at hand here, 1 over 1 minus x, this is a function that we can generally evaluate pretty easily arithmetically. We don't need power series representations to evaluate 1 over 1 minus x, to be clear. But this is a stepping stone to being able to use power series in our transcendental functions. So functions like e to the x, ln of x, sine of x, cosine of x, etc. All of those types of functions, the non-algebraic functions, those functions, we don't have very good tools for evaluating them. That's why, for example, with the trig functions, you learn specific angles on the unit circle. Not because those angles are magical, but because they're the only ones that are easy to evaluate, easy to figure out the values for sine and cosine. So in order to be able to evaluate those functions at any x value, we need something more powerful, and that's actually what we're going to be doing with these power series. And if you've ever wondered how your calculator actually computes the values of those functions, this is how it does it. It uses the power series representation for functions to approximate the values. Because, again, a power series is just a polynomial, an infinite polynomial, and polynomials are just adding, subtracting, multiplying, and raising to higher powers. And those are all things that can be done with arithmetic on a microprocessor level. Transcendental functions can't actually be evaluated just using 0 and 1 transistors, so you have to convert them to these polynomial approximations. Okay, but that's getting a little bit ahead of myself. I just wanted you to see the big picture here and what this is all about. Now we're going to use this function and this power series that we've found for it to figure out the power series for several other functions. So we'll start with just a basic example. So example 1, express 1 over 1 plus x squared as a power series. Find the interval of convergence. So one thing I want to notice is the convergence here, this is our convergence when the absolute value of x is less than 1. And this is from the geometric series theorem, right? We already proved that with a geometric series that the absolute value of x has to be strictly less than 1, or in other words, x has to be strictly between -1 and 1. And so that applies here to this 1 over 1 minus x power series. Now, in the past, when we first looked at power series, we used the ratio test to check for convergence. You're not going to be using the ratio test whenever you use this formula. Whenever I use this identity to find a new series, I don't need the ratio test because I already have the result from the geometric series test. So you would just be doing extra unnecessary work. Okay, with that in mind, express 1 over 1 plus x squared as a power series. So here's the trick. This is a variable, and I can always substitute out my variable. If this equality is true for all x, I can plug anything in place of x, and it will still be true. Now in this case, it's only true for all x less than 1, but that's okay. So instead of plugging in x, I'm going to rewrite this expression as 1 over 1 minus -x squared. So now I can plug in this -x squared into this formula. And actually, I'm going to do it in the second form, the n equals 0 to infinity version of the series. And so this is 1 over 1, sorry about that, the series from n equals 0 to infinity of -x squared to the nth power. So the key here, we're really just using the geometric series formula. But we're using it in a simplified form, right? It's like we've changed this to n equals 0 to infinity and r to the n. And we're just replacing r here in this formula. Now I do have to do a little bit of simplification. And the reason I have to do that is for future manipulations. So the main thing I always want students to do is to split off x to whatever power you're going to get away from the rest of your terms, because we're going to start dealing with differentiating and integrating power series, and we'll need that power term to be separated for that. So in this case, I have -1 times x squared to the n. That's the same thing as -1 to the n times x squared to the n. And that becomes the sum from n equals 0 to infinity of -1 to the n times, I guess I wrote x squared squared. That was x squared to the n. So this would be times x to the 2n. Now the question is, how do we find the interval of convergence? Well, before we were looking at the absolute value of x being less than 1, but now our r here, the absolute value of r, is the absolute value of negative x squared. And that has to be less than 1. Of course, the absolute value of negative x squared is just x squared. And if I take the square root of x squared, I get the absolute value of x. And the square root of 1 is 1. And so finally, our interval is x from negative 1 to 1. Okay, so that's our power series for 1 over 1 plus x squared. Let's take a look at another function. Find a power series representation for 1 over 2x plus 5. Find the interval of convergence. So again, my goal is to write this in the form 1 over 1 minus r. And then I will be able to swap this in to my geometric series form, n equals 0 to infinity of r to the n. Okay, so that's the real challenge to most of these problems, is figuring out how to do that, how to write it as 1 minus r. Well, the first thing I notice here is that I've got this plus 5, and I sure would prefer if this was a positive 1 instead of a plus 5. So what I'm going to do is factor a 5 out. And if I factor a 5 out, I get 1 when I factor the 5 out of 5, and then I get plus 2x over 5. And I can change this to 1/5 times 1 over 1 plus 2x over 5. Now, I'm trying to break this down into really tiny steps so that there's no confusion on the algebra, but after you do a few of these, you can skip 1 or 2 of these steps. You'll often be able to see a step ahead or so. Okay, now, this can't be 1 plus in the denominator. It's got to be 1 minus to identify the correct r. So I want you to write it as 1 over 1 minus negative 2x over 5. And now I can apply my series and make this the series from n equals 0 to infinity of negative 2/5 x to the n power, but we forgot a little something. I have to have a 1/5 multiplied in front of this series. And so, like I said before, I always want these series to be simplified a bit because you have to practice the skill of rewriting these so that you can use them for differentiation and integration. And so we've got negative 2 to the nth power over 5 to the nth power times x to the nth power. And I could split up that negative 2 to the nth into negative 1 to the nth times 2 to the nth. That would be fine too, but I don't really care either way on that one. Now I can take my constant and move it inside the sum. I can distribute it to the terms in the sum. And if I multiply 1/5 in here, I get 5 to the n plus 1 in my denominator. And then up top, we still have negative 2 to the n times x to the n. Now, as far as the interval of convergence is concerned, we know that our absolute value of r has to be less than 1. And in this case, that's the absolute value of negative 2/5 x. This becomes 2/5 times the absolute value of x, and this has to be less than 1, which implies the absolute value of x is less than 5/2. Right, and I just multiplied the 5, divided the 2, and now I can split my interval up into x being between 5/2 and negative 5/2, and now I'm done. Okay, let's take a look at another one. Now for this next one, it asks us to find a power series representation for x cubed over 2x plus 5. So I noticed that this looks a lot like the one I just did. Just did 1 over 2x plus 5. So I'm going to use my result from example 2 in this problem. So I'm first going to rewrite this as x cubed times 1 over 2x plus 5. So this becomes x cubed times the series that we found in example 2. And that series was negative 2 to the n over 5 to the n plus 1 times x to the n, right? Let me double check that. Yes. So now our variable for our sum is n. So I can, so x is a constant in terms of the sum, the variable for the sum. So I can move that x cubed inside the power series. And when we get x cubed times x to the n, that's going to become x to the n plus 3. Okay, and that's it. So, of course, again, just make sure you keep in mind that this result came from example 2. In general, you often be given problems where you don't already have the result for part of the series, so you'd have to do sort of both of these examples built into one problem. Now it asks for the interval of convergence, but remember, the interval of convergence came from the value of r. And the value of r hasn't changed here. We used the same power series with the same value of r, so we get the same interval of convergence, which was x between negative 5 halves and 5 halves. And that should make sense because if we look here, x cubed is just a number. So whether the series is finite or infinite doesn't matter, doesn't change if I just multiply it by a single number x cubed. It's about this infinite sum. That's the part that decides whether it converges or not. Okay. Moving on. So we're going to take a look at a theorem, and this is a pretty important theorem. But it's pretty simple at its heart. There's just like one or two little tricky things we have to be careful about. So theorem, the differentiation and integration of power series theorem. If the power series of the form the sum of c sub n times x minus a to the nth power has a radius of convergence equal to r, then the function f defined by f of x equals c naught plus c1 times x minus a plus c2 times x minus a squared plus dot dot dot, which is this power series, is differentiable. And therefore it's continuous and therefore also integrable on the interval from a minus r to a plus r. Its derivative is found by differentiating term by term, and its integral is also found term by term. So in other words, the derivative with respect to x of the sum from n equals 0 to infinity of c sub n times x minus a to the n is the sum of the derivative of the terms, which equals the sum from n equals 1 to infinity of c sub n times x minus a to the n minus 1. Okay, so if that was a whole lot, or it just like kind of hit you all at once, a lot of notation, that's okay, but pause for a second and think carefully about the following, because this is the tricky thing. My lower bound for this series changed to n equals 1 from n equals 0. This won't always happen, and that's really important. So we want to see, why did this happen? So let's go back up to where we wrote out this f of x long form. So this was the n equals 0 term, and n equals 1, and n equals 2, and n equals 3, and so forth and so on. And if we take the derivative for this function and we just write it out long form, we get 0 plus c1 plus c2 times 2 times x minus a plus blah, blah, blah. So what happened? The 0th term became 0, so it disappeared because it was a constant. So because the 0 term in this expression was a constant, it was x minus a to the power of 0, so we got a constant. That term disappears and it becomes n equals 1. That doesn't always happen. This is just our most general expression of the derivative process here. So you have to take a little mental step to check if your initial term for a sum is a constant or not. So what do I mean by that? Well, if I'd had the sum, say x to the 2n plus 1 from n equals 0 to infinity, then when I plug in 0, I get x. And then I get x cubed, and then I get x to the 5th, and so on and so forth. And so if that happens, my first term is not a constant. So essentially, all you got to do is always make a little mental check. Hey, when I plug in my initial value for n, do I get a constant or a variable? If I get a constant, then when I take the derivative, I got to get rid of that term. And if I don't, it's totally fine. Leave that term. Okay, so hopefully that makes sense. Now, we take a look at integration, and that's a little more straightforward. The integral of the sum is the sum of the integrals. And so when I do that integration, I get c plus the sum, c sub n times x minus a to the n plus 1 over n plus 1. Notice both of these, they're polynomials. So all of these expressions are just the power rule, right? This is the power rule for derivatives. And this is the power rule for integrals. Okay, so I actually already did the part explaining why the series now starts with n equals 1, but I typed it up again here, so it's a little cleaner there. Nonetheless, let's just reiterate here. Since the 0th term is a constant and is therefore eliminated when taking the derivative, it is extremely important to note, again, saying it again, I'm really trying to emphasize this because this is a super common mistake for students, that some power series may have 0th terms that are not constants. So in that case, they wouldn't be eliminated. In other words, you gotta check every time you take a derivative of a power series, whether that initial term is a constant or not. And our second crucial fact here is that although the radius of convergence will stay the same when integrating or differentiating power series, the convergence could change at the endpoints. So if I had convergence from -1 to 2, not including the endpoints, maybe when I integrate, or maybe when I differentiate, I might end up with, sorry, let me try that again. If I had, say, x greater than or equal to 1 and less than or equal to 2, and I differentiate the power series, my interval of convergence might change to say x is greater than strictly 1 and less than strictly 2. Something like that. So if you need to know whether a power series derivative converges at the endpoints, then you will have to check that separately. And of course, we already have previous tools for doing that. Okay, example 4 here. Express 1 over 1 minus x squared as a power series by differentiating 1 over 1 minus x. So what do I mean? Well, I know that 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n power. But I look at this 1 over 1 minus x squared, and it looks a lot like the derivative of 1 over 1 minus x. So let's just do that derivative off to the side. We'll compute it. The derivative with respect to x of 1 minus x to the negative first power. It's -1 times 1 minus x to the negative second power times the chain here, the inner derivative, which is -1. So the negatives cancel, and I get 1 over 1 minus x squared. So what does that tell me? That tells me that 1, so this implies 1 over 1 minus x squared is the derivative of 1 over 1 minus x, which is the same thing as taking the derivative of the power series. And so that gives me the sum of n times x to the n minus 1. And now we do a little check. When n is 0, I plug in n equals 0, I get x to the 0, that's 1. That's a constant. So when I take the derivative, the 0th term is going to disappear. And so this becomes the sum from n equals 1 to infinity of n times x to the n minus 1. So that's it. That's my power series representation for 1 over 1 minus x squared. All right, let's take a look at another example. Find a power series representation for f of x equal to tangent inverse of x and its radius of convergence. Okay, well, I look at this one and I go, well, what do I know about antiderivatives and derivatives for tangent inverse? Well, I know the derivative for tangent inverse looks like 1 over 1 plus x squared. So, if I know that, what does that tell me? So, the derivative with respect to x of tangent inverse of x is 1 over 1 plus x squared. And this thing here, 1 over 1 plus x squared, I can rewrite that to find a power series. It's got that 1 over 1 minus r form. And so this becomes the sum from n equals 0 to infinity of negative x squared to the nth power. And I can rewrite this as, remember, this is like negative 1 times x squared. This is negative 1 to the nth times x squared to the nth, which is x to the 2n. So I've got the derivative for tangent inverse of x is this power series. But I don't want the derivative for tangent inverse of x. I want tangent inverse of x. But that just means I take the antiderivative, right? If you take the antiderivative of the derivative, you get the function. So we'll just do that with the power series expression for the function. The integral from n equals 0 to infinity of negative 1 to the n times x to the 2n dx so this becomes x to the 2n plus 1 divided by my new power, 2n plus 1. And remember, we're talking about a series, we're talking about an integral here, so when we integrate, we've got to add plus c. Now remember, with the derivative, we could lose a term taking the derivative. With the antiderivative, we gain a term, but that term is gained on the exterior of the series expression, so it doesn't change anything about our subscript there. We don't have to worry about that when we're taking the antiderivatives. Now it said find a power series representation for f of x equals tangent inverse of x and its radius of convergence. I'll save the radius of convergence for the end, but I do want to know what c is, because if I want the actual power series that represents f of x, I have to know the actual value for c. And in this case, it's pretty easy, because I know the value when x equals 0 for tangent inverse of 0. And if tangent inverse of 0 equals 0, then this whole series evaluated at 0 plus c also has to be 0. So a little tricky thing, remember that for series, 0 to the 0 is 1. So you do have to check in your series when you go to evaluate, when you go to plug in n equals 0. If your initial term would give you a 0 power here, then you'll actually have a term that's equal to 1. But in this case, when I plug in n equals 0, I get 0 to the first power, which is 0. And all of the other terms will also be 0. So we get 0 plus c is 0. And that's great, because that means c is just 0. So altogether, I can just write simply that tangent inverse of x is the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1. Now, for the interval of convergence, we look at our radius, and our value of r would have been negative x squared here. And we're taking the absolute value, so we can just say x squared is less than 1. And when I take the square root, I really shouldn't write it like that. Let's say the square root of x squared is less than the square root of 1. But the square root of x squared is the absolute value of x. So the absolute value of x is less than 1, and so x is between negative 1 and 1. So now we've found our first transcendental function's power series representation. So this is a pretty big deal because tangent inverse of x is very hard to evaluate. You know how to evaluate it at a few key values like 0 and maybe 1 and so forth and so on. But in general, it's very hard to evaluate. But now we can use approximation techniques for series. In particular, this is an alternating series, so I can use alternating series estimation theorem to approximate the value of this function for any given x, at least any given x in this restriction. Now that's kind of a tricky part here. So we have this restriction for the interval of convergence. That's the only place we can apply these approximations. But we'll learn in our section on Taylor series and Maclaurin series how we can move the location of our approximation around, how we can change the interval. But we're not there yet. So let's just keep digging into this. Okay, so now we'll deal with another transcendental function, ln of 1 plus x. So we want to find a power series representation for f of x equal to ln of 1 plus x and its radius of convergence. Okay, so how do we do that? Well, again, this comes down to, do I have an antiderivative or a derivative for the natural log that looks like 1 over 1 minus r, kind of? And I do, because the derivative for ln of 1 plus x is just 1 over 1 plus x. And this is the same thing as 1 over 1 minus negative x. And so this is the sum from n equals 0 to infinity of negative x to the n power, which is the sum from n equals 0 to infinity of negative 1 to the nth power times x to the nth power. Okay, so now I don't want the derivative of the natural log. I want the actual natural log of 1 plus x. So I integrate. And of course, it's a power series, so all we're applying is the power rule. X to the n plus 1 over n plus 1 plus a constant. Okay, now this is totally fine. I would accept this answer if I asked a student to show me the power series representation for ln of 1 plus x or ln of 2 plus x or whatever. I would totally accept this answer. Not a problem at all. Should leave it in this form. That would be great. However, most of the time you will not see it written exactly like this. Most textbooks, I think, will use an index shift, meaning they're going to change the lower bound on the series and move it up to n equals 1 to infinity. And so we have to compensate. Everywhere there's an n, since I increased my index by 1, I compensate by subtracting 1 from every n. So it becomes negative 1 to the n minus 1 times x to the n over n. Now, if you plug in to this series n equals 0, and you plug in n equals 1 as your first term of this series, you'll see you get the same thing. You get the same values, just changed where they are. And the reason that a lot of books use this form for ln of 1 plus x is because it's a little bit simpler. Instead of having these n plus 1 terms, these both become just n. That's not a requirement. I'm not too worried about that. Either way is fine. Okay, but what is a requirement is figuring out what the value for c is. And again, this is another one where x equals 0 is an easy value to plug in. Usually that's the value we go with because the power series is generally easy to evaluate at x equals 0, at least this type of power series. So we get ln of 1 plus 0, which is ln of 1, which is 0. And that implies that the whole sum from n equals 1 to infinity of negative 1 to the n minus 1 times x to the n over n plus c. I should have plugged in 0 there. Of 0 to the n plus c is 0. But for this power series, evaluating at 0 eliminates every term, and so we just get c is 0. Now, both of the examples that we just did do result in a constant of integration of 0, but I don't want students to make the mistake of thinking that that's always going to happen. It certainly isn't. It just happens in these particular cases. All right, that's our power series representation. And finally, for the interval of convergence, we look at the absolute value of r. So we go back to when we made the series transformation. That was here. So r was negative x. That's got to be less than 1. So x is between negative 1 and 1. I guess I didn't really ask for the interval of convergence. I just asked for the radius, which is 1. So I don't really need to do that. I'm not asking to solve for the endpoints of the interval here, though we of course could. Okay, that's it for that one. Example 7. Evaluate the integral of 1 over 1 plus x to the 7th dx as a power series. Now, here's where we start to really see more of the value of this tool. I mean, it should be clear that we can now approximate certain transcendental functions using power series, which in and of itself is very, very helpful. But it also means that we can now deal with integrals that we couldn't deal with before. And this is a perfect example. The integral of 1 over 1 plus x to the 7th dx, you're never going to find a way to evaluate that integral directly. But I can rewrite it as the integral of 1 over 1 minus negative x to the 7th. And I can convert that function inside to the sum from n equals 0 to infinity of negative x to the 7th to the nth power. This becomes the integral of the sum from n equals 0 to infinity of negative 1 to the nth power times x to the 7th to the nth, which is x to the 7n. So just to reinforce this, even though we've been doing it for several examples, notice this is why early on I said, every one of these problems, I want you to rewrite it so that you get x to a power by itself. There's no other x expressions in it. And it's because everything else is a constant here. So when I'm integrating it, I really want this as x to a power so that I can just apply my normal power rule. So we take our antiderivative. We get x to the 7n plus 1, all divided by 7n plus 1. And then we tack on a plus c at the end. Now I can, of course, check the interval of convergence, or at least the radius of convergence. We've got the absolute value of negative x to the 7th. That's the absolute value of x to the 7th is less than 1. But, of course, if I take the 7th root of 1, I still get 1. So I get that x is between 1 and negative 1, or the absolute value of x is less than 1, whichever way you want to put it. So what that means is I can only use this power series representation for x between negative 1 and 1, but that can still be very useful. So let's take a look. Estimate the value of the integral from 0 to 0.3 of 1 over 1 plus x to the 7th dx correct to 8 decimal places. So that sounds like a crazy amount of accuracy here, right? 8 decimal places. So we've got 0.1, 2, 3, 4, 5, 6, 7, 8, and 5. So 8 zeros. That's a lot of accuracy. And you might think that we are going to need a whole lot of terms here, but let's take a look and see just how good these power series can be for approximating these things. So if I'm evaluating the integral from 0 to 0.3, I need the antiderivative. And I already have it. I computed the antiderivative in the previous problem. And what did we get? We got... I really didn't need as much space for that problem as I thought. X to the 7n plus 1 over 7n plus 1. Evaluated from 0 to 0.3. Okay, so I plug in 0.3. I get 0.3 to the 7n plus 1 over 7n plus 1 minus, and I evaluate the sum at 0, which I end up just getting 0 for. And so now the act of approximating the integral becomes the act of approximating this alternating series. And what do we know? We know that this series converges from negative 1 to 1. And the alternating series estimation theorem says that if you have an alternating series and you know it converges, you can apply the theorem. So that's what we're going to do, right? We're just going to jump straight in, apply the theorem, and approximate this thing. So alternating series estimation theorem. And we're going to start listing out our terms. So b sub n in general is the 0.3 to the 7n plus 1 over 7n plus 1. And it would be very hard to algebraically solve this expression to see which value of n we would need to use. So we're going to brute force it like we've done in the past. Okay, so let's do that. B0 is what I get when I plug in 0, which is just 0.3 to the first power over 1, which is 0.3. And B1 is 0.3 to the 8th power over 8. And so let me just throw that in a calculator. And so for that, I get approximately 0.12345 82012. And that's not smaller than the error we were asked for, but it's pretty small. So you can imagine we're not far off here. So let's try the B2 term. That's going to be 0.3 to the 15th power over 15. And so this gives me approximately 0.1, 2, 3, 4, 5, 6, 7, 8, 9. And then a 9, 5, 6, so forth and so on. And this is certainly less than the 0.00000000. 0.05. So what does that mean? That means that my integral, which I'm marking star here, star is approximately b0 minus b1, right? It's alternating. The 0th term is positive. The next term will be negative. And that's 0.3 minus 0.1820. I only need the 8 decimal places, so that's good enough. And so what do we get here? 0.3 minus this thing, which is 0.2999918 and 0. Okay, so that's it for that one. I mean, that shows you just how powerful these approximations can be, where you can ask for something like 8 decimal places of accuracy, and you can get it with just the first 2 terms of the series. All right. Well, that's it for this video. Thank you for watching.